Hello and welcome back to Physics 41, University Physics. Now the last lesson for this chapter. So let's first review what we have discussed so far in the previous chapters. So in the last chapter, we have discussed how to find the magnetic field of a current carrying conductor. And we actually used the law of Biot-Savart. And the direction of the magnetic field just can be found using right-hand rule. So direction of the finger is your thumb is the direction of your current, represents your current, and your fingers represent the magnetic field, actually curling around the direction of the current. Now, you are just trying to find the magnetic field near a long straight current carrying conductor equation, just approximately, or the law of Biot-Savart, the magnitude for that matter, just reduces to this very simple equation, mu naught I over 2 pi r. So for this lesson, we will be discussing the magnetic field of current carrying. So this is a current carrying loop, and if you are trying to find the magnetic field at the axis of the loop, then it's given by this equation. So n is the number of loops, I is the current, A is the radius of the loop, and x here, the distance, the x distance from the center of the loop. So this is the magnetic field at the axis of n loops. So if you look at it, the direction at the center or at the axis of the loop is actually uniform, straight line. And off axis are the directions outside the axis. So it's actually curling. So you notice that it's actually curling around the wire, or curling around the at that center or the axis of the loop. The direction is actually uniform. It's just one direction. Okay, so in our case, we'll just consider the very simple case at the center of n loops. So at the center of n loops, that is at x is equal to 0 at the center. So this equation will then reduce to this equation. Very simple equation. Mu naught ni over 2a. Again, n here represents the number of loops. Number of loops need not to be an A. An A here is the radius of your loop. So for such a loop, the direction at the center is governed by, again, guess it, right hand. So if you curl your fingers and that's the direction of the current in the loop, then the direction of your thumb is the direction of the magnetic field of the current loop. So these are represented by these images here. So what are the applications of the field of a current loop? So of course you have the electromagnet. So in order to make an electromagnet, you just connect a current carrying, or say a conductor. You form it into a loop, forming what we call a solenoid. Then you connect it to a battery, any source of EMF. And that basically is a magnet. It becomes a magnet. In this case, it's called an electromagnet. So if supposedly in the normal face-to-face na class, you will actually be making an electromagnet. Sadly, can't be done because of the new normal, because of the pandemic. But essentially, you will do it like this. You will. By the way, from our equation, sorry, it's not a vector, it's just a magnitude. The magnetic field at the center of current loop just mu naught Ni over 2A. You will notice that the magnetic field is directly proportional to the number of loops and to the current. And it's inversely proportional to the radius of the loop. So if you want to make a very strong electromagnet, meaning an electromagnet with a strong magnetic field, then your number of loops as large as possible, as many as possible. Your current should be as large as possible. In order to do that, you need a very large battery. And your radius, since it's inversely proportional, your radius should be as small as possible. So in the class, you will actually wind your loops or your wires in a ball pen or in a pencil, or a much better thing is to wind it in a metal conductor such as a nail, because a nail is a ferromagnetic material. If you expose it to a magnetic field such as the magnetic field of a current loop, then all of its magnetic moments, dipole moments, will align with the field, and that the magnetic your conductor or your metal will have a magnetic field that will add up to the magnetic field of the current loop, essentially making it more magnetic, making it more stronger. That one. So in this example, you have a magnetic wire actually wound in a nail, a metal nail, and connected to just, I think so, just AAA batteries. Yeah, batteries. You will notice that has attracted a bunch of paper clips. A bigger scenario of this is the electromagnets found in junk shops. So this is the way junk shops differentiate metallic objects in the junkyard or scrapyard. Use a very powerful, very big, or very large electromagnet. So another example, sorry, another example where you can find current loops in an atom. So in an atom, there are electrons looping around, rotating or looping around the atom. So essentially, the reason why everything have magnetic dipole moments, matter has the magnetic dipole moments, because of electron current loop. And if this electron current loops, if all of the atomic magnetic dipole moment or molecular magnetic dipole moments align, then for a human, you can do that. If you can align all of your magnetic dipole moments inside your body, basically you become Magneto. So Magneto is basically just a source of magnetic field. You can align magnetic dipole moments. That's just fictional. You can't do that. So again, this is a model of an atom. The white circles here are electrons. The red circles are the protons. Blue ones are the neutrons. You will notice that these are essentially electron currents, and they are forming a loop. They're looping around the atom, essentially creating a magnetic field. So it just so happened that in a neutral atom, these current loops produces magnetic fields that are misaligned, such that they become zero. So how about the Earth? How does the Earth have a magnetic field? So the Earth also has its own current loops. So essentially, at the core of the Earth, it's actually uh, liquid iron. Outer core of the Earth is actually made of liquid iron, and inside this sea of liquid iron are ions, ions, positive, negative ions. And these ions, since the Earth is rotating, so these ions will go with the rotation of the Earth, and they will form the current loop. And this is what creates our planet's Earth's magnetism. So ions rotating because the Earth is rotating, so they form current and essentially generating the magnetic field of the Earth. Okay, so let's test your understanding. So we'll only consider, in our case, magnetic field at the center of N loops of a current loop. So arrange the electromagnets from strongest to weakest. So electromagnet A is this. It's connected to a AA battery. It has 16 windings or 16 loops, and the radius is 4 centimeters. Electromagnet B is connected to a 9 volts battery. It still have 16 loops, but the radius is smaller. It's centimeters. And electromagnet C, still 16 loops, and the radius is smaller, but the battery is only AA battery. AA battery is 1.5 volts. These two are 1.5 volts. This is 9 volts. Okay, so we can take out the number of loops in our analysis because they all have the same number of loops. So we'll just consider the current and the radius. So in order to have a strong magnetic field, you need to have a large current and a small radius. Large current means in order to have a large current, you need to have a large battery. In this case, B has the largest battery, and it's also has the smallest radius, meaning B will be the strongest. Then, since as compared to compare A and C, just have the same battery, meaning they have the same current, but the radius of C is smaller, making it smaller radius, larger magnetic field. So C will have a larger magnetic field at the center as compared to A. So the arrangement here will be B, C, A. B is the strongest, is in the middle, A has the weakest magnetic field, or is the weakest electromagnet for that matter. So let's now go to some examples. Okay, so calculate the magnitude and direction of the magnetic field at point P due to the current in the wire. So your wire here has 3 segments. You have this segment here, straight segment, and then a loop, half loop segment, and then another straight segment. So we need to take into account the contribution of all the segments. So for the straight segment, we will use law of Biot's bar. So mu naught over 4 pi integral of I or dl I cross r dl over r cubed. So for this straight line here, that's our I direction. Our r is the distance from the wire to the point. Since we are trying to find the magnetic field at point P at the center of this, will be our r. So our I is here, our r. So I cross r, they are parallel. So meaning I cross r is 0. So this straight line segment will have no contribution. Magnetic field due to straight segment at this point P here will be 0. Similarly, for this straight segment here, even though its r is direction up to the left, but since I cross r, two parallel or anti-parallel vectors, the cross product of two parallel or anti-parallel vectors will always be. So the contribution of the straight segments in this example, non-existent. They have no contribution. Essentially, this problem will just reduce to basically a half loop, just one half loop. Okay, so what's now the magnetic field of the half loop? So it's just very simple. So B just mu naught n I over 2a. The value of n is, since it's half loop, so the number of loops is 1/2. I is given 2 amperes. The radius A is given as R, 1 meter. Solvable. So that's it. You can now solve. I just want you to continue this because it's an obvious problem. Okay, let's have another example. 2 half loops. Okay, this one is more interesting than the previous example. To calculate the magnitude and direction of the magnetic field at point P in terms of R, I1, and I2. And what happens when I1 is equal to I2? Okay, so the upper, take note, the straight segments will have no contribution at point P because it's parallel to point P, straight segments. So the first half loop, we have already solved this in the previous example. Now, for the second half loop, by the way, we forgot to solve for the direction. Sorry. Magnitude and direction. We are asked for the magnitude and the direction. So using that formula, you can solve for the magnitude. But how do you find the direction? So the direction of the current here is in this direction. So meaning your fingers are the direction of your current. So the direction of the magnetic field at point P will be into the page. Direction here will be into the page or into the plate. That one. You can also define your axis so that you can specify the direction in terms of unit hat vectors. But the direction into the page will suffice. So going back to the second example. Okay, so the current in the upper loop will have a direction of into the page, or will have a magnetic field directed into the page. The current in the lower loop will have a direction of out of the page. So since the loop is the direction of the current in this loop is counterclockwise, the direction will be out of the page. So say if we define the magnetic field direction to be in the direction of positive k hat if it's out of the page, and if it's into the page, the direction is negative k hat, then due to wire number 1, the upper loop, the direction will be negative k hat, and due to wire number or loop number 2, the direction will be direction of the magnetic field at point P will be positive k hat. Okay, so the total magnetic field now at point B will just be due to magnetic field due to wire number 1 and wire number 2. Wire number 1 is just mu naught I1 over 2 pi. They have the same radius A equal to R, and the direction is negative k hat into the page for wire number 1. For wire number 2, mu naught I2 over 2 pi A, where A is still R, they have the same radius, and the direction of this is k hat. So simplify mu naught over 2 pi R. Will have I'll just write I2 first, positive. The negative sign, I will incorporate that to I1, so minus I1. Then I will take out all of the k hat out. I2 minus I1 k hat. So this is now the answer to our problem. Calculate the magnitude and direction of the magnetic field at point P in terms of R, I1, and I2. R, I1, and I2. So the second question is, what happens when I1 is equal to I2? So when I1 is equal to I2, so it becomes 0. This term here becomes 0 when I1 is equal to I2. So meaning the two opposing magnetic fields will cancel each other. Oh, I thought we only have two examples. We have a last example. Oh, sorry. Oh, 4 examples pala. Okay, I will not solve all of these examples. I will just start the solution for you to substitute and find the final numerical value. Okay. You have example 3, current and magnetic field of current loops. You have a closely wound circular coil with radius 2.40 centimeters. That's 800 turns. What must be the current in the coil if the magnetic field at the center of the coil is given? Okay, so this is just very easy. So you are still use the same equation. U naught N I over 2A. Magnetic field is given. Number of turns or number of loops is given. Radius given. So the unknown is current. What is the current in the loop? Given ang magnetic field at the center of the loop, given a number of turns, given ang radius, solve for I. Solve for I, cross multiply, you will have 2BA over U naught. Okay, substitute all of these values, substitute B, that one, substitute A. Need to convert this into meters. It will be 0.024. And then mu naught is just a constant, 4 pi times 10⁻⁷ Tesla meter per ampere. Number of loops is, and then you will get your answer. Just a very easy. Last example. Okay, this is interesting. So you have two concentric loops. And you are asked to find the magnetic field at the center of the loop. Take note, this is basically just one whole loop, one whole system. So they have the same current flowing through this loop. Again, the straight line segments, these segments here will have no contribution. Basically, this is just the magnetic field due to two half loops. So similar with what we did in example number 2. Okay. So the two loops have different radii. So essentially similar with example number 2. So the magnetic field will just be due to loop with the radius A, a small loop, plus loop with the radius B, larger half loop. So this will give you mu naught. They have the same N, but they have the same current, but they only differ in the radius. Radius of A is 8. So due to the smaller loop, again we will define the magnetic field that is coming out of the page as positive k hat, and the magnetic field that is going into the page as negative k hat. So due to this smaller loop here, a loop A, the loop with radius A, current is flowing counterclockwise, so meaning direction of the magnetic field is out of the page or positive k hat. For the second vector, magnetic field, this larger loop here, it's just mu naught. They have the same number of loops, 1/2. N, for both case, N is 1/2. They have the same current I, but they have different radii, so B. And the direction for the magnetic field at the center of this second loop, loop B, the direction of the current is clockwise, then direction of the magnetic field will be into the page, negative k hat. So factor the common terms, mu naught Ni over 2 pi, and then you will get 1 over A. Then the negative sign, I will incorporate that here, minus 1 over B, k hat. So given your A's and B's, the magnitude of the magnetic field here, actually the final magnetic field, will be out of the page because 1 over A is always because A is always smaller, the radius A is always smaller, meaning 1 over A will be bigger than 1 over B always. So meaning this will be a positive value, positive k hat. And it makes sense because the loop A is closer to point, or has a much smaller radius, smaller or closer to point P as compared to larger loop. So substitute all of the given values and you will get your magnetic field at point which is directed out of the page or out of the plane. So that's it for this lesson and basically for this chapter. So that ends the chapter on the sources of magnetic. I will see you again in the next chapters.